Welcome to The Explainer. Today, we're bringing some serious energy, pun absolutely intended, because we are setting the stage for a truly fascinating journey. We're going to dive into the mechanics of exactly how we power our modern world. But more importantly, we're going to uncover the massive, hidden waste behind the devices we use literally every single day. I mean, from a tiny glowing bug in your backyard to the colossal power grids spanning entire continents, energy is constantly transforming all around us.
Okay, let's dive into this. Just look at the sheer global scale of our energy consumption when you see Earth lit up at night. You've got billions of artificial light bulbs illuminating vast areas of our planet, constantly transforming electrical energy into radiant energy just so we can see in the dark. It's undeniably stunning to look at, but it also represents a colossal input of power that we somehow have to generate, transport, and consume nonstop.
But it really begs the question, how good are we at actually using all that power? Well, let's look at a pretty striking juxtaposition. On one hand, you have the classic incandescent light bulb, a piece of human technology we invented over 150 years ago. On the other, you've got nature's own design, the bioluminescent firefly. Now, be honest, have you ever accidentally touched an incandescent light bulb that's been on for a while? Yeah, it burns. And honestly, that intense heat is a massive clue about a fundamental flaw in our artificial design.
Now, what's really interesting about this slide is exactly where the energy in that bulb actually ends up. A staggering 95% of the electrical energy fed into an incandescent bulb is just transformed into thermal energy, heat. Just 5% becomes the useful radiant energy, the actual light we're paying for. Look, we turn on light bulbs to illuminate our living rooms, not to cook our dinner, right? So that massive 95% chunk of thermal energy is completely wasted.
Now compare that sad 5% to nature's design, 88%. That is the incredible efficiency of a firefly. A firefly's tiny little body takes 4.13 joules of chemical energy from its food and transforms it into 3.63 joules of radiant energy. That's the greenish glow in its abdomen it uses to attract a mate or hunt prey. So nature's biological machinery is transforming energy with 88% efficiency, just completely blowing our classic human technology out of the water.
So here is how we're going to break this down today. 1. The efficiency illusion. 2. Measuring energy waste. 3. Non-renewable energy sources. 4. The renewable future. And 5. Conserving our power. We're going to zoom all the way out from that single glowing bug to our cars, our grid, and finally what we can personally do about it.
Let's jump right into section 1, the efficiency illusion.
So the crucial point is unpacking the actual math behind how machines use and lose power. Efficiency is, quite simply, the ratio of the useful energy produced, which we call energy output, to the total amount of energy used, the energy input. You just divide the output by the input, multiply by 100, and boom, you get your percentage. But here is the absolute golden rule of this equation. No energy transforming device on Earth is 100% efficient. Something, somewhere, is always lost in the transaction.
Now, engineers are constantly trying to hack those percentages to be better. Take fluorescent lamps, the long tubes you see in offices or schools. They're a huge step up from the incandescent bulb, actually hitting an efficiency of up to 25%. They give us the same illumination, but waste way less electrical energy. But there's a catch. Fluorescent lamps contain mercury, which is highly toxic. So we solve one efficiency problem, but we kind of create a brand new environmental headache if they aren't disposed of properly.
Moving on to section 2, measuring energy waste.
Let's scale up from light bulbs to the machines we use every day. Think about transportation. A simple human-powered bicycle absolutely destroys modern vehicles in efficiency. It transforms your human kinetic energy into forward motion at an insane 90% efficiency. An electric vehicle sits much lower, somewhere between 24 and 45%. But hey, it still easily beats a gas-powered car, which is limping along at a really measly 8 to 15%. And actually, fun fact, even nature isn't totally perfect. Photosynthesis, the process literally keeping plants and everything else alive by turning radiant energy into chemical energy, is only about 5% efficient.
But it's important to remember, whenever you see those efficiency numbers drop, like that 8% efficient gas car, where is the rest of that energy going? The answer is almost always heat. Thermal energy is by far the most common form of waste. Friction in engine parts, resistance in electrical wires, it all just bleeds away as heat. Unless, of course, the device you're using is literally an electric space heater. In that one highly specific case, the thermal energy is exactly what you're asking for.
Which brings us to section 3,
non-renewable energy sources.
Now that we've established how woefully inefficient our machines can be, we need to talk about where all that massive input energy comes from in the first place. The core difference to grasp here is the timescale. On one hand, we have non-renewable resources. These take millions of years to form, meaning they can't be replenished anywhere near as fast as we burn through them. On the other hand, we have renewable resources, which are virtually inexhaustible or bounce back quickly through natural cycles.
And this brilliantly illustrates the point. It is wild to think about what you are actually burning when you flip on a natural gas stove. Natural gas is mostly methane. And just like coal or crude oil, it's a fossil fuel. That means it is literally the compressed, decayed remains of prehistoric plants and animals that lived anywhere from 100 to 600 million years ago. They captured solar energy back then, died, got buried, and cooked under pressure for eons. Once we burn up this ancient supply, it is gone for good.
Another massive non-renewable source is nuclear energy. Think of places like the Pickering nuclear plant in Ontario. Inside those huge concrete domes, a process called nuclear fission is happening. Engineers force the nuclei of large, unstable atoms, like uranium, to decompose. This releases an absolutely massive amount of potential energy, which turns into thermal energy, heating water into highly pressurized steam to spin turbines. It's wildly powerful. In fact, this one non-renewable process generates about 52% of Ontario's entire electrical energy.
Let's look forward to Section 4, the renewable future.
So what's the game plan when those non-renewables dry up? Well, our greatest renewable asset is literally shining right above us. Scientists estimate our sun has about 5 billion years of radiant energy left to give, making it virtually inexhaustible for our purposes. We can harness this directly through passive solar design, like architects cleverly putting big windows on the south side of a house to capture heat. Or we can actively harness it using photovoltaic cells, solar panels. These use modified silicon to transform radiant energy directly into an electric current. And since the sun takes a break every night, we just pair these panels with batteries to store the excess juice for cloudy days. But we aren't just relying on the sun, we can tap into the perpetual motion of the Earth itself. Hydroelectricity is actually the largest renewable energy producer globally right now. It uses the water cycle, driven by the sun, to fill high-altitude reservoirs, and as that water rushes down, its kinetic energy spins massive turbines. We're also capturing the kinetic energy of the wind with turbines, tapping into deep underground heat with geothermal plants, and even placing turbines underwater to catch the heavy kinetic energy of the ocean's rising and falling tides.
Let's move to and see how this builds into our final segment. Section 5, Conserving Our Power.
All right, we know how the grid works, but what can you and I personally do about it? First, we actually need to clear up a major physics misconception. You've probably heard of the law of conservation of energy. It states that energy is never created and it is never destroyed. It only transforms. The total energy in the universe stays exactly the same. So if energy is never destroyed, why do environmentalists tell us we need to conserve it? Well, they mean avoiding waste. Even though the amount of energy doesn't change, its usefulness totally does. Highly useful electrical or chemical energy is constantly degrading into useless, unrecoverable thermal waste. That's why we have to conserve it.
And the cool thing is, practical conservation isn't just about redesigning billion-dollar nuclear plants. It is deeply rooted in everyday, personal choices. Things you have direct control over today. Turning off the lights when you leave a room. Actually switching your devices fully off instead of letting them bleed power in standby mode. Taking slightly shorter showers. Running the dishwasher only when it's completely full. Hanging your clothes to dry. Using a simple fan instead of cranking the AC. Or hopping on a bus instead of driving. Every single one of these choices directly reduces the demand we put on those ancient fossil fuels.
Which brings us to our final thought for today. If the undeniable laws of physics dictate that energy is never truly destroyed, why is it so absolutely vital that we conserve it? The answer isn't about saving energy from disappearing from the universe. It's about taking responsibility. It's about preserving the useful energy we still have and protecting the incredibly fragile planet we extract it from, before all of our hard work simply slips away as heat. Thank you so much for joining me today, and as always, keep questioning the world around you.